Awesome. Hey, everybody.
Hi.
Welcome to Contributing Today. I'm Cassie Brevu. I am a cloud developer advocate at Microsoft. I'm super excited to be talking to you today about machine learning, and I am here with Annalene.
Hi, everyone. My name is Annelien, and I work as a cloud architect at Microsoft as well. I work on the Belgian market, and I'm really very excited to hear more today about both TensorFlow and PyTorch, as I use it quite a lot with Belgian clients and abroad.
Awesome. So today we have two amazing speakers. We have Gus Martins, who's going to give us an intro to machine learning and how to use TensorFlow. He is an advocate at Google working with TensorFlow. And then we also have Ari Bornstein, who is going to be giving us an overview of PyTorch Lightning, doing some audio classification. So I will hand it back to you, or Annalene. Sorry about that. And you can give us an intro to Gus.
Thanks a lot. So first of all, don't forget to use the hashtag contributing.today. And the speaker I'll be introducing is named Gus. He will talk to you today about TensorFlow. He's a senior developer advocate at Google. So he will talk about what TensorFlow is, a little bit more about the framework, why is it important, how can you use it in a development environment, and what tooling do we use generally. Also, some interesting links will be shared. And of course, he will mention how you can contribute yourself and add code to TensorFlow.
Hi, everyone. Can you hear me?
Hi. Yes, we can hear you.
Nice. Hello, everyone.
One more thing I wanted to add, we do have a code of conduct. We're here to learn cool things and be kind to each other, so let's do that. And the recording will be available at the latest tomorrow, so if you want to rewatch some of the awesomeness that you learned. So I'll pass that back to you, Gus, and you can get us started with some cool TensorFlow stuff.
Of course. Hi, everyone. Can you see my screen? I guess it's nice. Hi, everyone. So my name is Gus. I work on Google as AI developer advocate. And today I'd like to talk to you about TensorFlow, of course, which is what I do. I use TensorFlow every day, all day long. But I also talk a little bit about how the open sourcing works and how you can contribute to that. But before we get there, I'd like to first, let me organize my stuff here, sorry. Let me first start. So this is what we're going to talk about today. We're going to talk a little bit about machine learning. We'll talk about TensorFlow, community in OSS, and some examples where people are using machine learning, so to give you some ideas. Before we go into that, let's go to what's machine learning. So given, I was talking to the team before, and since not all of you are experts on what's machine learning, what's this kind of thing, how does it work, I decided to give a brief introduction. Of course, you're not going to become an expert, but you understand where are the differences, and I'll try to go over some of the terms that people use so you can understand better the rest of the presentation. You're probably a developer, so you kind of understand how coding works, right? So you go and you write your rules, and then you pass data through it, and you get answers. This is what developers do, right? So here we have an example of a function doing something. We give data, we get answers from that. If we extrapolate a little bit, games are also very clear, right? We have the brick game here. We can calculate the ball trajectory and stuff like that, calculate points. And so this is a good example of what's traditional programming. You write your rules on any language you want, and then data comes, go through your rules, and then you get the answers. So that's the basic idea of traditional programming. When we start to talk about machine learning, we are changing things around. So how does it work is, instead of writing the rules, they might be too complex for you to write. And we'll get into that in a little bit, but the idea is you got the answers and you got the data, and then you give it to a machine, and the machine will write the rules for you. So that's basically what machine learning does. It figures out all the rules for you. And this looks like kind of magic, and that's a little bit like that, but there is a lot of very interesting developments in terms of computer science that made this possible. Let's go into an example. So if you want to do activity recognition app, you might just use, for example, speed as a variable in your code, and then you can just do, I don't know, if its speed is less than 4, you define that the person's walking. And if you want to also have another state which is running, if it's more than 4, it's running, right? This is easy. If you want to detect if the person is riding a bicycle, maybe we can change a little bit our if and else there and add some more rules, and then we can do walking, running, and biking. And this can go on, but it cannot solve every problem. For example, if the person is doing golf, right? So how can we create a rule that will say, oh, this person is playing golf? How can we do that? And the answer is that that's not easy at all. And that's where we come back to our visualization of programming. And we can see here that the traditional programming is not going to solve that problem easily, right? That's where we are going to come back to machine learning and try to answer that question. But now the question is, how do you get answers and data? So we come back to our activity recognition app. And if we use the information about accelerometer, gyroscope, and everything from your phone, for example, and those are, let's represent that as those numbers, what we know is if we get this information and we label them as, oh, I was walking during this time, and this is the information from my phone sensor, and I was running at this time, and then you give that information. So you label that properly, and then you just go and they say, and give that to the machine. It will train a model that can figure out that there are patterns on your sensor information that can indicate with certain precision that you are walking, that you are running, or biking, or golfing. So this is something that you cannot do by hand. That's really, really too hard. So this is what machine learning is here for. Let's take a better look into that. So how does this work? Okay, I have the data, I have the labels, and now how does the machine understands and give you an answer? How does that work? Let's try to see the process around here. So at first, what the machine does is it will, when you start training a model, that's what training a model is. When you start training a model, the first thing the machine will do is get some data and make a guess. It will guess, receive some sensor information, guess it's walking, it's running, for a lot of data. The next step is you see how close to the proper answer is the machine, right? So the random guess will give you whatever accuracy it is, but you measure that. You have to measure. So is it too far? Is it too close? Am I close to? Is the machine random guesses close or not? After you measure that, you can come back to the machine and say, look, you made some mistakes and you are super far. Can you try again try different answers here? And you keep repeating this process on and on and on. So this is the process of training. The machine will make a guess, and then you measure its accuracy, right? Measure how close it is to the answer. And then you get these answers from the machine, and you optimize them. And optimize them is saying, hey, you are, let's say you're giving values too high, values too low. Maybe you should, and then the machine will figure out, oh, I'm guessing too high number, let's say, and then you try a lower one. And you keep doing this with your data for some time until it gets to a point that it can, based on your data and on the labels, it will make absurdly good guesses. And then the accuracy will drop, and you have like the loss of you will drop, and you have a very good accuracy. And that's the process of training a model, right? So we'll come back in here, and just to have another view on what's going on there, you give data. This is the first drawing there is the training process. You give answers, data, the machine process, and give you rules. The other part of that is using those rules, right? And we call that inference. So after you train a model, you have a good model that you train for a long time, and then you can use that for inference. Using for inference is giving data to a model the model will run on this data and give you an answer. So for our activity recognition, you will start walking with your phone. The phone will detect, oh, you're walking. That's one inference, right? And doing training is much slower than doing inference, of course. So we need to understand these two steps because it helps you understand where you can deploy your model and what's happening on your deployment environment. So you have training where you create a model, and you have inference where you use your model. Those are the basic concepts about machine learning. I'm not going to go into details on the math behind it, how it works. It takes a while, and I guess we don't have that much time. And let's try to understand how TensorFlow can help you with that and why that would be a good thing to learn. First of all, what is TensorFlow, right? So TensorFlow is a framework that helps you build machine learning models. It's open source, free, and end-to-end. In this end-to-end is very important. I'll come back to that in a little bit. And it's start developing here at Google, of course, and then we open sourced that in 2015, and it's been under heavy development since then. Last year, Jeff Dean is the VP for TensorFlow. Last year, he published this one. If you can see there, it's on 12th of May, and we had passed 100 million downloads, right? And this is cool and all, lots of downloads since 2015. But as of this year, we are already on 200 million downloads, and we have more than 52 million views on our tutorials and guides on tf.org, almost 10 million views on our blog articles, almost 10 million views on our YouTube channel, and we have more than 800,000 learners on Coursera and Udacity courses around. So this is a good thing that there's a lot of people using TensorFlow as of today. What are the goals of TensorFlow? Make machine learning easy, simplify as much as possible, and still give you a super powerful tool to be available even for the top researchers or for developers or for anyone that's trying to use that. And of course, be as scalable as possible to be able to train your models on multiple machines, as training some models might take days, right? It can go from, 5 minutes here in your machine to days on data centers. So this is not something that you can do in any way you want. You have to think about that so you can even finish training. And who are the people we pay a lot of attention to? So first of all, researchers. And here I mean researchers in terms of those people that are pushing the boundaries on machine learning itself, right? So computer science and people that are studying machine learning, trying to create new models, new architectures, solving new kinds of problems. These people, we of course aim to have an amazing tool for them. We of course pay attention to enterprise, which are the big companies that want to use machine learning to, for example, detect outliers, detect fraud, to do sentiment analysis on their with their clients, with the users of their apps, and there are others. And of course, we pay a lot of attention to developers because these are the main people that will use TensorFlow, right? And if we think like researchers, there's a bunch of people. Developers are way more people, and we want them to be able to also use this powerful tool, right? So we pay a lot of attention to these three groups of people, and to give them the tools they need. And when I say tools, there's a lot of them. So as I mentioned, TensorFlow is not just a library for machine learning. It's a complete framework that goes from creating your model that we can see on the left side there, I guess it's left, where we have TF datasets, we have Keras API, we have distribution strategies, and we have a lot of toolings to deal with performance, to having a model repository. For example, we have TensorFlow Hub, where with 2 lines of code, you can already use a model, right? Download a state-of-the-art model and use that on your pipeline, on your app, wherever you want. And we have also the deployment side, where you can deploy your model on a server to create an API, or you can deploy that on a mobile device, on your phone, Raspberry Pi, on an iPhone, or you can deploy on a browser, or on a Node.js server, or on an Electron app, or you can even use the model with a bunch of languages of course, C, Java, and so multiple others. So we have the tools to get you all the way from all these boxes. And let me go a little bit in, explain some more of the tools. Aside from those, we also have a lot of extensions that are created by researchers, created by community. So here we have a lot of those, and they help you build models, help deploy models, help tune models to help you get proper solution for your problem. So we have, for example, one example here is TF agents. That's one extension to help you create reinforcement learn agents. So reinforcement learning is the part of machine learning that you, if you see those cool news about, oh, machine learning won the Go match, won the chess match, won the StarCraft match. So those are reinforcement learning agents, and that does that. So it's a little bit different from what I explained to you, but it's the same idea. And TF agents can help with that. And there's a bunch of others. We have TF quantum, so you can try to deploy your model using quantum machines, and so on and so forth. Multiple tools. So it's not only those I mentioned, there's a lot of those. Aside from that, we based our API on a Keras API. Keras is a API by itself, but we use that as our main API on TensorFlow, right? So you can see Keras over other frameworks, and it's the same API that we use on TensorFlow to make things easier. It's if we have enough time, I can show you a little bit of that, but the idea is to make understanding a neural network easier, right? Because it's it can get really complex really fast, so we try to make this as easy as possible. This is our main API. Let's take a look on some real-world applications and where people are using machine learning these days. Of course, Google used that on a lot of places. The maybe most common use of machine learning is maybe Gmail with a spam filter. We have, of course, recommendations. We have battery analysis on Android to help you get more from your battery. We have a lot of things. I'm not going to go into details on those. Of course, Google search has a lot of machine learning behind that. Assistant, of course, but all of them, there's a lot of apps using. Let's take a look on 3 of them. The one in the left is called Hold For Me. It's a feature from Pixel devices that, I don't know, when you call somewhere and then there's the music that you have to keep listening while nobody gets the phone on the other side, because the queue, there's a lot of people in the queue, you are number 10, you have to wait, and then there's a music. So what it does is you use this feature and it will listen the music for you, and then you can do something else. When someone picks up the phone on the other side, the phone will ring you and say, hey, someone is here, and then you can come back to the phone. So it allows you to do other stuff that's not listening to that music. Aside from that, of course, we have Google Translate that you can point the camera to a text. It will run some OCR, which is getting text from image. It will figure out which language it is, and after that, you'll translate to the language you want. So that helps you with a lot of things, like, for example, reading a menu in another country. Or seeing signs on the street, lots of things. So Google Translate does that. Of course, machine learning. And we have also the HDR Plus camera from Pixel devices also that does HDR Plus uses machine learning just as the night vision, where you take pictures on a very dark environment and it will make it better for you. All of this is machine learning, and this specifically runs completely on your device. They work completely offline. If you put airplane mode, all of them will keep working, right? So you don't need any connectivity to make them work, which is also another advantage here. Aside from that, we have another example that was published last year where the ZSL, which is the zoo here in London, they have, of course, a research center, and they use audio detection to detect when there are shots in the forest, in specific, I don't remember the country, sorry, but they detect shots so they can, when someone's shooting, because those might be poachers hunting for animals, so they can send the rangers there to look into what's going on. So this is something that helps, because it's very hard to monitor a forest, as you can imagine, right? It's too huge. So if you have these devices, if you have these sounds which they track, and then they can figure out where poachers attack most, and then they can put their rangers around there. So they used TensorFlow, and to be more precise, they use a model called YAMNet to detect this and help them fight poachers, right? So this is a cool example. There's one example that was posted today, by the way. So there is on Pixel phones, you have a car crash detection, which what this does is whenever you are in a car, and for what I hope nobody ever needs this, but if you're in a car and there's an accident, and the phone will detect, and if you don't press something to stop it, it will call emergency and bring help for you. And this is something that what was posted today is that there was a driver that was got into a trouble, and the phone called the emergency and got to him, and he was super happy with that. And here we have an example of how we train those models. As you can see, multiple phones in the car and with a dummy, and it crashes and they get the sensor data so they can create a model. So this model is super interesting and it can really help, right? So because it has to figure out that if you are in a car crash instead of dropping your phone, right? It has to figure that out, and that's what they did. So this is a very good use case. And last one, just to be more uplifting instead of car crashing, we have this bunch of experiments and demos from the Magenta team. Magenta is a library in TensorFlow that helps you deal with art, right? So music, images, and sound that helps you be creative. Here, the specific example I'm pointing out is the Sketch RNN, where this demo specifically, you can go there and you can get the computer to help you draw anything. So here, you can start drawing, for example, a fire truck, and the machine will complete for you, right? Which is really cool. This is a very, very nice example of using machine learning just to play around with that. Of course, maybe you can argue that's not the most useful, but it's fun to learn and it's fun to play with it. My daughter loves playing with that. There's another link that I shared. That's the experiments.withgoogle.com/collection/AI, which have a lot of very good demos of using machine learning to do cool stuff if you want some ideas. So this is that. And then we got to the point where, okay, this looks interesting. How can I contribute or be part of the community? So in terms of contribution, as you can see the graph there, even in 2020 where things were crazy, there is a lot of contribution from third party. People are always helping improve the framework, and that's amazing. And how can you contribute to TensorFlow? There's multiple ways. Of course, the main one that people think is code. You can write your code. And this, of course, it's challenging in terms of the framework is really big. And contributing, you have to understand a lot of code. So there, if you follow that URL there, there's some tips on how to get started, because you can find some easy problems and start from there and build up. But not only code, you don't need to do only code, right? You can, for example, improve some tests, create some more tests for some functionalities you're using. You can help with documentation. You can help translating documentation, which is absurdly important. That makes the framework better for a lot of people. You can add example notebooks, for example. If you did a cool example and you want to share, you can submit a pull request to the repository. You can help review and comment other pull requests. Report issues whenever you find something. Please report them. Star them whenever you think they're important. This really, really helps improve the ecosystem, improve TensorFlow as a whole. Also, a cool thing that helps and contributes to TensorFlow is whenever you, do a blog post, paper, article, or social media, you talk about machine learning and you use TensorFlow, just mention that so people see and can come with questions. That really helps. If you want to contribute even more, of course, transparency is very, very important. We do everything in the open for TensorFlow. And one thing that if you want to do a bigger project that's not only fix a bug or improving some logs, you can create a new feature, and we have a process for that, which is we have RFCs, requests for commenters, where you can create one and discuss with the community your idea and go from there before any coding. Of course, there's these, we have a lot of those. We have, I guess, 80 going on right now, or So for multiple projects, improving multiple parts of TensorFlow. So just go create, if you have a big project, for example, I don't know, bring, I know that's hard. Improve creating a new component for TFX. I don't know. That you can bring a RFC that is very specific for you, and then people help you write that better to have a more broad version. And then after it's accepted, you can just code that and help improve. This is one thing. Of course, I mentioned about translating, creating more resources in other languages also helps a lot. And we have translations from the community for 13 languages, I guess. So there's a lot of people contributing to the documentation. We, of course, this is hard. It's not for anyone to just go there and translate or use an automatic tool. There's a lot of nuance there. I guess machine learning is not there yet to translate all the docs, so this really helps. Aside from that, we have specific interest groups, SIGs, right? That does with specific parts of TensorFlow. And what does it do is like a community that talks about a specific part of TensorFlow. So here, for example, we have all of these already going on. They have monthly meetings. So we have a SIG for TFGS. TFGS is the library to run TensorFlow models on the browser, right? So they have a interest group that people come, discuss new features, discuss what's going on, share. So they do that every month. You have one for TensorBoard, which is the debugging tool, let's say. It's how you can understand how your model is behaving. So this is important too. We have multiple, and you can join one of those groups, or you can create one of those if there's a specific need. And then from there, you can create RFCs or even map the community around them, around those specific areas, and you can contribute there. So in summary, TensorFlow as a framework for machine learning to solve real problems. Use it in a lot of places. I give just some small examples, some cool ones, and we'd love to have more people be part of the community and help play with that. And that's it. And I have a question for the organizers. How long do I have? Hello? 15 minutes. Okay. Okay. Let's do something. Let's do something really fast. I have one example here. Oops. If you want to go to this URL here. Yeah, sorry, I didn't copy that. Let's see. Nice. So let me give you one example of how to run, just to train a model, right? So this environment that I'm here is called Colab. Colab is a IDE, let's say like that runs completely on that runs on the web. And what it does here, it gives me a IDE, and all the code is run on VMs on Google Cloud, right? And this is free. You can just access and play. This is completely free. You can just go and play with that. Just follow the URL that was posted. How can that be free? This, of course, has some limitations. You don't have the super amazing, most advanced hardware, but you have GPU access, you have TPU access, which are very specialized chips to train machine learning. Let's go into some here. What I'm going to do is I'm going to create a model that does solve this equation here, right? Of course, you can say, oh, but this is very easy. I can do a code for that. Yeah, that's completely true. But let's start with somewhere first, right? We cannot fly before we crawl. First thing we're going to do here, we're going to execute this. So what's this doing? Okay, yes, I agree. Run anyway. It's from Google. I guess I trust them. So here, what I'm doing is I'm running this. So since it's the first cell, it's first connecting to a VM somewhere. And I can see some more details here, but I'm not. So, and then I'm, of course, this is all in Python. So if you don't know Python too much, you can read and understand. Just bear with me. So here we are going to just do the regular imports, putting the dependencies we need. And the main one, of course, here is TensorFlow. And from there, we are going to use something called Keras, which is the API. And here we're going to create a model. Model is basically, this is a neural network, and my neural network will be just one neuron. So what I'm trying to do here is, remember the machine will make a guess, we measure accuracy, optimize, guess, accuracy, optimize. The machine will make a guess of one number. It will try to find one number that given one input, and that number you can get an output. That's all the machine is going to try to do here. So it's absurdly simple. So let me do this again. I don't know if I did, but it doesn't matter. And then we need to compile our model. When we compile our model, we are telling TensorFlow, look, to do the accuracy, we need a loss function. We need to know how far we are from the correct answer. To do that, we're going to use a loss function called mean squared error, which is a very basic one. If you did any kind of math in your in college, I guess you've seen this. Again, not going into details into the math, but this is a simple one, and it will tell you how far you are from an answer, from the correct answer. And SCG is a stochastic gradient descent, which is how you tell the model, hey, you are your values are too high, your values are too low. This is how you tell the model how to optimize, how to fix their answer. Let's do this. I don't know if I did. And now we need some data. I only use this six points as data. So this is our data. Remember, I give data and I give labels. The labels are these ones, right? So the equation I'm trying to do is y is 3 times x minus 1, right? Is it? Plus 1, right? This is what I did. Let's see the data here. You can see here those dots. Those are the data. So this, we have the x, which is the data, and we have the y, which is the label, right? Now we just train a model. Poof, let's do here. We are train this for 500 epochs. What does it mean? Remember when I mentioned in the past, make a guess, how far you are, optimize, try again. So every time you do this once, this is one epoch, right? So we are trying that for 500 times. It's, since this model is absurdly simple, it's very fast to finish. And here we have it. It's ready. Our loss is super, super low. So if we try this, let's think which should be the answer here. Okay, let's pretend nobody saw that. If we try to use the model, this is when we call model.predict. This is the part, the inference part I mentioned. Remember, I give now a new data, and the model will use what it learned to give me an answer, right? So this is the predict for 10. We should expect, let's go back to our equation. PPP, 3 times 10, 30, plus what, 31. So let's suppose it will give me 31, right? Let's execute here. And it gives me almost 31. And this is something you have to learn about machine learning. This problem specifically is a regression problem, right? I'm trying to find a number. I'm not trying to classify in which if it's a dog or a cat, which is very basic. I'm trying to find a number. It didn't give me exact number. And machine learning is not about exact numbers anymore. It's about a number that's very close to the main answer. If we keep training for more epochs and with more data, we might get closer and closer to 31, but that's not something we are aiming for. We don't aim to super precision. We aim to a number, and we give you like accuracy. You can say, oh, this is 98% accuracy. And then you have to learn how to deal with that. This is another part of machine learning, how to deal with the answers you get, right? It's not like it's not as precise as regular programming. Let's take a look on our equation here. If we plot, the green here is our equation. And this is the simplest code you can do with TensorFlow, right? We just trained a model to solve this equation here. If you can play with that, change whatever you want. This Colab by itself is a great place for you to play with stuff and learn, because you can just keep changing. When you don't want to use this anymore, just close the tab and go. That's it. And of course, this machine will be claimed back after a couple of hours. And if it detects that you're not using it, you just tell you, look, you're not using, I'm going to close, blah, 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 close, and give the machine to someone else. So this is, don't worry, play, change whatever you want, copy, make a copy to your drive, put on your GitHub, doesn't matter. Play around with that, and this is an amazing tool. This is simplest code TensorFlow you can write, and that's it. Go back to the presentation. Colab, I mentioned. I could go over the explanation, but I prefer to use the code to do that. And thank you very much.
Presentation. Thanks a lot. I think I really like that you started with the machine learning paradigm. You talked a little bit about the batch and real-time inferencing, but I was really surprised to see the nice examples and the demo in Colab. Indeed, the OCR, I see myself a lot in real life with clients all over the world. But the car crash versus the dropping phone example for me was really interesting, because I think often people don't really realize how often we already use these types of technology to such cases. There are plenty more of examples, like real-time license plate recognition and so on, in which TensorFlow and or other frameworks can be used. So we do have some questions already.
Oh, nice. Of course.
I think the first question was, what is JavaScript TensorFlow.js?
So TensorFlow as the framework for you to build your models, first of all, it can be used for a lot of languages. For example, you can use from C++. You can load a model in C++ and use that. The difference for TensorFlow.js, for TensorFlow for JavaScript, is there's two things. You can create a model exactly like I did in Python. You can do that in JavaScript. Same thing, very similar API. Or you can get a model from TensorFlow, regular model, convert TensorFlow.js. And why would you convert? Because the model you use in your browser, remember, it's running on your browser. It's not running on a server that's connected to your browser. It's on your browser. So the model has to be downloaded to your browser. Given that, this model cannot be like a 1 GB model for language understanding, right? It has to be way smaller. So when you convert this model, the same thing is for phones. When you convert this model to run on TensorFlow.js, the TensorFlow.js library will be able to load this into memory, and then you can do inference. So there are a bunch of examples where you can do face tracking with a lot of dots, and then you can move your face and it will move Barack Obama's face. I don't know, mirroring your face. Or there is one cool model called Iris. I forgot the complete name. Which it does is it knows how far I am from the camera, given the size of my eye. So that's the kind of thing that would never be able to do with proper classic programming, let's say, right? Because it can measure, and it does for all different people. We are all different. It can do that. And there's a lot of other, they can do hand tracking and all those kind of things. Everything you can do in TensorFlow can do also on TensorFlow.js. And since we have an amazing JavaScript community, right? I guess they would like to play with TensorFlow too.
Okay, thanks a lot for your answer. A second question is around the SIGs. So Kubernetes has SIGs for topics like mental well-being as well. The question is, are there also TensorFlow SIGs for not really directly technical topics?
That's a good question. I don't know if there is, but if you think that's a good idea, I would definitely suggest you submit to us hey, I want to create this SIG for mental well-being and or other related stuff. That's definitely something we want more people to do. And yes, if you want that, please send an email. We can work on that.
Okay. I myself really was very happy that you very briefly touched upon the subject of reinforcement learning, because reinforcement learning is a technology that's starting to be used more and more often, but it's really only good in very specific environments. And I was wondering, in what type of environments do you see use cases in which reinforcement learning is used? And do you have anything to say in that space?
Well, there's for reinforcement learning, the main use case that people think about is playing video games, right? So you think, I'm going to create a bot to play video games. But then stay with me. So you can play a video game, right? And then what's the value for a company to have a bot playing their video game super well? And then I'll tell you one value. First of all, testing your game. If you have a bot that can play your game super well, you can leave it testing your game non-stop, like stress testing and finding stuff. So if it plays like a proper human being, if you can make it play closer to, instead of being super good, being just human, you're going to find multiple patterns and say, oh, maybe you should improve here. It's slow. There's a bug. Also, maybe something you could do is there's a bunch of things you can do on that, on quality for games. That's one, right? Another thing is recommendation system. A recommendation system can be built around reinforcement learning because it's a system that's hard. All recommenders are hard, right? We can do one with that will learn your behavior or the behavior people like you, and then can tune the kind of notifications we receive, the kind of products we receive. So reinforcement learning can also help on that. And the other thing is reinforcement learning can help you on other parts of machine learning. So for example, when I talked about StarCraft, right, they build a bot. It's not all reinforcement learning. It's impossible. There's a lot of other models working together to have one agent that can win. So that's also cool. It's not like reinforcement learning will solve by itself, but it can work with other supervised learning models to help you solve problems. So this is this. Oh, one other example for games. As you can see, I play some games. There's one specific use case that I don't know if you've been playing against someone, and they drop. They drop. All of a sudden, they drop for whatever reason. Connectivity. Their mom's calling them for dinner. I don't know. Whatever. So that's annoying, right? Because now you might win, whatever, but it's. So what if there was a bot that can continue their play style?
Okay.
And just continue. There doesn't need to be. I don't want to beat the hardest AI. I want to compete with the person I was competing already. It's the same level. So it's not being superhuman, it's being human. And this is something that I imagine people might be doing that already, but that would make online gaming better, right? For example, if you're in a team and then someone drops, you are automatically in disadvantage, right? Unless you're a Daigo. But if you're not Daigo, you're going to lose. The thing is, if there is a bot that can come and just replace that person and not be a dead body there, just help you, you get a better experience. You don't even need to know that's happening, right? You might know later if the person tells you that they drop, but then keeps your experience better. So this is the kind of thing that reinforcement learning can help.
Thank you for the examples. I have one example myself that I'd like to give because it's totally different. It's actually a drone that's in the water and it scans boats. And so it takes pictures of boats, and when it detects a crack, but the probability is not high enough that it's really a crack in the boat, so let's say it's 0.75 accuracy, then it will automatically take new pictures until the accuracy is either high enough or low enough for the other algorithm to be sure whether it's a crack or not. And I'm really very impressed by how reinforcement learning these days is popping up more and more. Yeah. I think another hot topic nowadays is model transparency. Is there anything specific that you need to do or that you already have that can help with that transparency, especially especially for example, public sector and so on? This is also a question that comes back often.
So there's when you talk, this is more in the field of responsible AI and how you can have a model that's fair, that has it's fair to everyone, that takes privacy into account, that's not biased into some people, for example. So we have a complete responsible AI toolkit on TensorFlow.org website where we can help you create model cards. Model cards are like explaining what our model does and tell you, look, this model does A, B, and C. It's good for this situation. It's not good for that situation. It has these bias maybe from the data set. It has, and they give you all the information whenever you use a model. It's like medicine, right? You read the medicine, you say, oh, this is not good if I am I don't know, if I just swam, if I don't know, anything like that. So the model will give you this kind of information. Look, this model is good for A, B, and C. So the model card is a good thing. We have a TF privacy that helps you understand how to train your model in a private way with taking privacy into account. And this is a hard problem because not every model can be trained with privacy in mind. But it can tell you, look, without retraining your model, it can tell you how good it is dealing with privacy. So you can imagine, I don't know how much that affects EMEA or Europe in general, but for example, in some countries, you can calculate credit, how much you can lend to someone, right? Imagine that database has address. Address is absurdly biased, right? Because if you live in a poor neighborhood, you're automatically tagged as I'm not going to lend money to this person. So how can you take that from your data, from the analysis? Because people think that's no, you have to have that. That's important. That's not important. That's a bias that we have with us, right? Having that's very easy to exclude a complete neighborhood, right? But it's not how machine learning should be used. So we have tools for that.
Okay.
Can I add something into the
course.
ethical side of this? I think when you said that last thing you said about it's not how machine learning should be used, I think there's a lot of things where not only checking that the model is fair, but also asking your question, is it ethical to even use machine learning in this situation? Like I've had people ask questions about using it for hiring algorithms or different things like that. And I'm just like, I don't think it should ever be used in hiring. And that's my opinion, but it's just, there's too many possibilities for discrimination when there's already so much unconscious bias within hiring already. And so I think when you're starting to do machine learning and you're starting to think about problems, it's not only making sure you're excluding those features that could attribute to issues, but also asking yourself first, should I even use machine learning for this?
I guess the machine learning is I was discussing with someone that's way smarter than me that machine learning is like a magical hammer, right? That you can nail everything. The problem is some things are not proper nails. And so what happened there's, for the hiring specifically, there is an algorithm for that. There was a blog about how amazing it is. And then someone got, okay, that's first of all, when you see that the model can detect a good hire, can detect your gender, can detect if your age, there's a bunch of those that are absurdly biased, but people think that they really work. So there was for hiring. Someone did that, and then someone, oh, let me test that. And then you're on a Zoom call, right? Or Meet or whatever, VC. And then the scores, when they put books in the background, are way higher with the same person, same position, they just change the background with books. That's a clear bias there, right? It's that your algorithm is not telling you anything about the person aside from, oh, there's a book in the background. That's not a hiring criteria, at least not that I know, right? Unless, I don't know, you're trying to hire someone that has books in the background, then might be a good thing.
I think, yeah, I mean, these algorithms that help with hiring or not hiring people are used a lot, I know. But I think in the end, it's all about balance, because sometimes we as people might even be more biased or biased in a different way than algorithms. So the fact that we can combine both our human perspective and something that's supposed to be objective, but might not always be, it's really nice evolution.
It is, but it's tough, as Cassie mentioned. And the one thing is that sometimes when people say, "Oh, there's a bias here," and sometimes I read about this every day, right? Even sometimes people say, and is there something here? And then you think a little bit and say, "Oh, got it." And then so it's not always obvious what's the problem, but as soon as you figure that out, you should at least, oh, look, there's a problem here, and then you tell other people. So that's how you learn, right? Sometimes it's not obvious, you just tell and help fix.
Well, thanks a lot for the talk and a nice conversation. I will give the word to Cassie.
Thank you. Yes, that was a wonderful introduction to machine learning. You covered so much topics, even from the art side, like talking about the Google Magenta, which I've played with before and I love. And there's just so many things you can do with it. With machine learning and with TensorFlow. And so our next guest, we're going to look at another open source library that you can use called PyTorch. So we are going to be talking to Ari. Ari actually used to be on my team at Microsoft, and now he is a fancy lead of a developer advocacy team working on PyTorch Lightning. So I'm excited to see what you're going to talk to us about. I know it's something about audio classification. Is that a spoiler? Did I just do a spoiler?
So a little bit. That's just one of the demos, but we're going to be talking about a lot of stuff. We're going to go start high level. We're going to go a little deeper. We'll open things up to questions and we'll make it interactive, and I'll show some demos and everything. I'm going to start by sharing out my screen. So let me know when you guys can see my screen. Okay. And I will start my presentation. So here, one second. Perfect. Are you guys all seeing my screen and everything's good? Cassie? Yeah, I just wanted comfort. All right, good. Sorry. Perfect. So let's get started. Perfect. So I'm going to be talking today about a topic that's a little bit more in depth around the area of machine learning and deep learning. I'm going to be talking about how you can optimize your deep learning applications without the boilerplate. But don't worry, we're going to have a little bit for everyone. So if you're new to machine learning and you're new to some of these concepts, there'll be a lot of stuff that's accessible for you. But also if you have a little bit more of a background and you're looking on how to take your deep learning applications to the next level, I'm hoping that there'll be a lot here for you as well. So before I get started, let me introduce myself. My name's Ari Bornstein, and I am the head of developer advocacy for PyTorch Lightning and Grid.ai. I'm originally from Washington, D.C. in the States, but I've been living here in Israel for the past 5 years. I did my undergraduate degree, a dual degree in history and computer science in a school in Baltimore, Maryland, where I did my undergraduate thesis in medical document classification. After that, as Cassie mentioned, I've spent about 7 years at Microsoft doing different open source engineering and cloud advocacy roles focused on the AI and ML space. In addition, over the past 2 years, I've been finishing up my master's in natural language processing at Bar-Ilan University as part of the BIU NLP lab, where I did a lot of research in the topic of multi-document representation, co-reference, and semantic embeddings. And recently, as Cassie mentioned, I joined Grid.ai to be the head of developer advocacy for both PyTorch Lightning and Grid.ai. So I think Gus gave a really good introduction to ML, but just in case some people are coming in now, I'm going to start high level and just clarify generally the space and kind of cut through some of the buzzwords around what's AI, what's machine learning, and what's deep learning. So to get started, we have the area of artificial intelligence, which is a general space around how do we model intelligent behavior. In here, we have tons of different methods beyond just machine learning, things like game theory, formal languages and formal logic, even dynamic programming that you might have learned in your undergraduate computer science degree. All of this falls under the field of artificial intelligence. Within artificial intelligence, there's a sub-branch called machine learning that we've been talking about. Within machine learning, there are many different types of methods. So there are probabilistic methods, there's graph-based and tree-based methods for doing the different tasks, and there's even methods that are not considered deep learning, but they also use what are called neural networks. And then within machine learning, there's a subset of algorithms that use neural architectures that we've been talking about, and these are deep learning algorithms. So typically when you're writing deep learning algorithms today, you don't just go in Python or in C and start writing in Scratch like you used to. You use deep learning frameworks. And the two most popular deep learning frameworks are TensorFlow, which we had a great introduction to in the last session, and PyTorch. And what I'm going to be talking about today is a little bit off the beaten path of not necessarily comparing TensorFlow to PyTorch or going through PyTorch, but what I'm going to talk about is a new topic, which is the challenge of the deep learning boilerplate. So some of you guys might be asking yourself, okay, that's cool, but what is deep learning boilerplate? What is boilerplate code, and what does that have to do with PyTorch? Well, deep learning in computer programming, boilerplate code are different sections of your code which are repeated in multiple places. You use these patterns a lot with very little variation. And when you have really verbose languages, they require programmers or developers, and this happens a lot in deep learning, to write out a lot of a code to accomplish otherwise abstractable functionality. And that code is called boilerplate. Now, where this gets even more complicated is within this abstractable code, it's very easy potentially to just abstract out the code, but because deep learning is such an area of research, it's very easy to accidentally abstract code and then lose flexibility, and you really need flexibility to go in deep. So we're going to talk about what happens when you have a lot of boilerplate in your deep learning code. You have a lot of challenges. The first challenge is reproducibility. If I have a lot of dependencies and I have a lot of this code and everybody's implementing it differently, it's very hard for me to just take your code and run it and understand how it works. Often, when we talk about model hubs or model libraries, one of the challenges we have there is that we think of models just as a computational graph of operations inside of a deep learning framework. But in reality, there's a lot more to it. The way that you load your data, the way that you transform your data, the way that you apply your data, also the different configurations that you set, all of those tie into what makes your model, and also how to train and get the same results. So if everyone's implementing these things with different variations, reproducibility becomes an issue. Another example of this is in a lot of frameworks like TensorFlow and like PyTorch, different implementations might take advantage of different hardware. So for example, I might have two models that do classification of cats and dogs, but one model uses CPUs and one uses GPUs and one uses TPUs. And because the implementations of how to integrate with that hardware is different, when I go now to kind of aggregate the models or take code or concepts from one, it becomes really hard to integrate it into the other one. So the next challenge that I face is reusability. Like, how do I link code? This becomes a bigger challenge in terms of boilerplate too, because I can give all my methods many different names. And so then I don't necessarily know exactly what and where what's happening in different code that's doing the exact same thing. So for many people, this is a major barrier in deep learning. If you've ever gone online, GitHub, and started opening up like for the original implementation of BERT and trying to read the code and understand, it's very different than the implementation for OpenGPT. And then there's a lot of different variations and tricks, and they're in different parts of the code, and they have different function names. And so a boilerplate affects readability as well. And the last challenge is reliability. When everybody is implementing the same types of code or the same patterns again and again and again, it's very hard to guarantee the quality of that code, or that code is encapsulating best practices. And in fact, due to the complexity, it's very easy to make mistakes. So one of the interesting blog posts that I was reading recently was by Jason Addick, who created a really cool framework called Deoldify that colorizes images. And he was talking about, in his original iteration of his model to colorize these images, he was getting this weird blending of colors that he didn't expect. And it turned out that a lot of that came from the fact that when he went to evaluate his model, he forgot to change it from from training mode to evaluation mode. So you can imagine that this boilerplate can be overwhelming and cause a lot of errors. And so where PyTorch Lightning exists, and why I'm so excited about it, is it exists to address the challenges of boilerplate. So you might be asking yourself, okay, cool, I've heard of TensorFlow, I have some familiarity with PyTorch, but what's PyTorch Lightning? Well, PyTorch Lightning is a way of organizing PyTorch. So to make coding complex deep learning research models simpler. It enables those things like reproducibility. It enables those things like being able to reuse code. It enables readability, and it also enables best practices, which we'll look at in just a minute. So to better understand this, we should look at Lightning's design philosophy. And this breaks down, I'm going to break this down into three major components. So the first component is that Lightning, you should standardize your research code. And in order to do this, you need to modularize. You need to decouple models and your data code from your baseline to increase the reproducibility of your application. So what does this look like? Imagine we have our project. I can actually give you a real world example. I was interested in doing audio classification. So I read this really cool blog post. I looked online. I said, okay, how do I do audio classification with PyTorch? And this was a couple months ago, and I found this really cool blog post here that shows, okay, here's how you understand data. Here's how you look at the data set. Here's how you pre-process things. It gives a really good background. I see a ton of code here. And I want to understand exactly what's going on in all of this, right? Within this code, like if I want to go and try to like reproduce it, it can be a little noisy. So we can actually look at the full notebook here, and you can see that while this implementation is cleaner than most implementations, there's still a lot of boilerplate code. The way that I declare the models, the way that when I have my training loop, the way that I have to set my device type, and the way that I have to change things, it's very easy for me if I want to now modify and play around with this to ruin this model. So I was thinking, what if there's a cleaner way to organize this code where it's the exact same code, but more organized, and then I can gain by not having the boilerplate. And so to start with, imagine this is all the code we have. And what we want to do is we want to abstract out what code is the research code and what code is related to our data. So we're going to do that here. So the first thing that we do is we have our deep learning code. Our deep learning code, and we extract out the research code. And this goes into a construct called the Lightning module. So this is what manages all the research code in my model. The next step is we have our data code, and this is all the code for data pre-processing, knowing how to test and do train splits. Because remember, if I take just a model from a model hub, I don't know how the data was processed on that model. So when I go to train that model on my own data, I might get different results. Now I can go through and read through a complex research paper, but often a lot of that data isn't included in the research paper. So by abstracting that out into a Lightning module, it becomes something that becomes standardized. And then the code that's left over from the Lightning module and from the data module, this is the remaining boilerplate. These are the common practices or the common patterns that we see in pretty much every single deep learning application. Things like your training loop, things like figuring out how to manage ranks when you're doing distributed training. And what PyTorch Lightning does is it manages the boilerplate for us. And here is where, honestly, this is where when you're developing deep learning applications, or when you're trying to take somebody's code that just runs on GitHub, and then you're trying to figure out how do I modify it or change it, this is where things often go wrong. So what PyTorch Lightning does is it manages that all out and abstracts it into a concept called the Lightning Trainer. So this is our first design principle, this idea of standardizing our research code, separating out the research code from our data code from the remaining boilerplate. Now, the next step is, it's awesome that Lightning is taking care of this boilerplate for us, but as researchers, we want to do crazy things. We might have different ideas. We might want to do something that's off the beaten track. And often when you're using, very simple abstract representations of models, it becomes very, very hard because all these details are abstracted out from us. So the second aspect of the Lightning philosophy is, while we standardize and abstract out the boilerplate, everything should be accessible and overridable. You can override what you need. So for example, if I want to do something like create my own custom loss function or play with the inner details of an optimizer, I should be able to do that and override that functionality, but I shouldn't have to. It shouldn't be forced on me. The next and last aspect is providing the AI best practices. So once we take out all this boilerplate for you, what we want to do is we want to make it so that all the best practices that for training your applications, the things that get your model to converge, that get your model to scale, that you don't have to worry about all the overhead of implementing each of these tricks in all these different ways. These come in as built-in features within the trainer. So things like multi-GPUs, multi-node, TPU training. Instead, if it's one of these really interesting things in deep learning, both in PyTorch and in TensorFlow, and when you want to go and start doing distributed training or use a GPU, you have to modify all your code. You have to make sure that it's using .CUDA. You need to make sure all these things are working. But if somebody else has another implementation and they're using TPUs, if I want to combine different components of these different parts of the different projects, I can't do that because I have to convert every single line of code. So what the AI best practices do here is they enable you to get a lot of these best practices out of the gate. So let's actually look at what this gets you. And one of my favorite parts is, let's start with distributed training. So what I have here is I have my model, which is a basic classifier. I have a data module, which loads up the MNIST data set, and I have a trainer. To train my model, all I have to do is trainer.fit. I pass in my model and my data module. This is pretty standard. If I were to go online, I can find 100 examples of MNIST. But now let's say I want to run this on a GPU. Today, if I'm doing standard PyTorch, I would have to go into this MNIST classifier and into this data module, and I would have to change the device on every single line of code. Maybe somebody made it a little bit cleaner and abstracted it out, but there's no guarantee. It's not standardized. What Lightning enables me to do is, because it abstracts out the boilerplate, if I want to train on a GPU, all I have to do is pass this argument, GPUs equals 1. Now, imagine if there's more than one GPU on my system. Now it gets even more complicated. Typically in PyTorch, I need to use the distributed trainer, and I need to manage process ranks, and I have to deal with things like race conditions, and I have to figure out how do I accumulate all my gradients when they're distributed across multiple devices. And so what ends up happening is you find a lot of code that could, or a lot of research projects that, given a little bit more GPU compute, probably could have scaled, but they get abandoned because people who are getting started or who want to, they don't have the capabilities to kind of abstract this out. With Lightning, it's as simple as just setting the flag GPUs to 8. And automatically Lightning manages, because I've abstracted out my data module code and my model, it manages everything I need for batching my data, for managing all the distributed ranks, for managing the compute in the back end, and just making sure that my model trains. Additionally, imagine I want to take this now to the next level and train that model on 256 GPUs. Traditionally, this is really hard. It's not only do I have to manage one GPU and manage all the different processes on one GPU, but then I need local ranks and global ranks. With PyTorch Lightning, it's as simple as GPUs equals 8, num nodes equals 32, and now my model, without changing a single line of my training code, is scaling to 256 GPUs. We get a ton of other built-in amazing best practice features as well. So one of the things that you can do when you're training a model, there's this concept of precision. Typically, when we have tensors or we have our data, there can be stored as 32 bits, or they can be stored as 64 bits. There are different levels of precision. But what we find is on many applications or many types of models, you can actually reduce the size, the significantly reduce the amount of computation time and compute by reducing the precision of your model. Now this, again, in standard deep learning, this is very hard, because if somebody implements one thing using one implementation of a component that I need with 32-bit precision and another one with 16-bit precision, I have to manually go through and understand exactly what they did to merge these two code bases together. Because that's abstracted out, if both are using Lightning, I can just pick and choose the code and combine it as I need. And in the trainer, I can just, if I want to use 32-bit precision, I use 32. If I want 16 for mixed precision, I just set it to 16. And this also can run on top of different backends as well. So you can imagine there are a lot more really amazing features here. I'll go through a couple others. So some are like automated model sharding. So this was a feature in the 1.1 release. This allows me to take, when I'm doing distributed training, to also distribute the memory and break up my model and distribute it across multiple GPUs and multiple instances. And by doing that, just with this one flag, I can reduce the memory overhead of my model by up to 50% in some cases. And then here, like, I get all these other features as well. So automated checkpointing, things like automated integration with logging with TensorBoard. But what's really interesting is, let's say I'm using Azure ML, right? And I don't have TensorBoard integration. I can actually add multiple loggers like TensorBoard, MLflow, Neptune, Allegro. There's many different loggers that I can integrate with. And then in my code, because it's abstracted out, I just have to use the .log function once, and PyTorch Lightning will manage integrating and logging across all the different platforms that I want for me. Additionally, when we're training, we might often run into bottlenecks. I might train a model, I'll be wondering, why is this taking so long? So PyTorch Lightning provides a profiler, which can show me on each of the hooks and each of the functions in my code how long they take and what their mean duration and total time is. And additionally, in the 1.2 release that actually just came out last Thursday, we provide native integration into PyTorch's profiler as well. So in addition to finding the bottlenecks within the different training hooks within Lightning, you can actually see it at a low level as well. And one of the amazing things about this is, again, we have a strong community, so the code is rigorously tested, and we make sure that it runs across different environments, whether that's Windows, Mac, Linux, and different Conda versions as well. And we try to make sure as well on obviously on different compute platforms. So when we were talking about readability before, there's a model for self-supervised learning. It's called SimClear. If you go online and you start looking for SimClear implementations, let's do that. So we can go into Google Research and we have a SimClear implementation here. See how there's my model utils, objective. There's a lot going on here. It's very, very hard for me to understand how the training and how this model actually works, right? There is training, and then there's when it's not training, and there's a lot of overhead here. And one of the challenges here is that because there's so many different ways that I can implement this, no two implementations look the same. But when you're using a standardization like Lightning, and I'll go back to my presentation here, you can see that when I want to understand what this model is doing, everything's just abstracted out into the interface in my training step. So here I can see that I have 2 encoders. I can check like for my item, like what it's an instance of, and then I have my 2 projections. and then I have the loss that I apply on the two projections with the loss temperature, return the loss, and my code becomes very clean. So one additional element when we're talking about reusability is this enables me now to share these components across projects and models, and because I don't have to worry about the boilerplate, I know that if a callback runs on one version, on one, I know if a callback works in a version of PyTorch Lightning, it will work in, I can take code that's in one repo and apply it to another repo. So here we can see, like, for example, if I want to put an adversarial callback here that tries to trick my model by coming up to that for MNIST that classifies a digit, and I want to create like an adversarial input to trick it to make a wrong decision, I can create a callback here for creating essentially confused logics. It applies the same interface. And then in my data module, I define my data module, I define my classifier, I do fit. And then here I can actually, in my trainer, I can provide this callback. And because it works in this trainer, this will also work for other models as well. So these callbacks and this functionality becomes reusable across different projects. And there are plenty of different amazing features, from accumulative gradients, stochastic weight averaging, model pruning, and the lottery ticket hypothesis, gradient clipping, debugging, early stopping, JIT export, Onyx export. There's a memory profiler, integrated integration with metrics, speed profiler, truncated back propagation, and just a ton of like amazing features that if I were as like a developer to go take one version of PyTorch that I found on the internet and like implementation of a model that I found on the internet and then try to put these features in, it would be extremely hard for me to do. But if they're using PyTorch Lightning, all I have to do is play with the flags of the trainer, and then I can optimize and quickly experiment and apply best practices to any model that's using PyTorch Lightning. So there's a large ecosystem. You can see that a lot of the top companies and organizations and research labs in the field are using and building on top of PyTorch Lightning. We have a global dev community with over 406 contributors, and we're always looking for more. And I want to show a couple community examples, because as an advocate, I always want to be able to kind of showcase work that's being done by the community. And let's take a look. So recently, one of the things that I did is I went through some of the different projects and I put together these posts, and we'll share them in the end in the links, of different projects and different domains that that definitely inspired me, that I thought were really cool, and that you can actually look at to inspire your next project. So for example, in natural language processing, we have a model called Unitary Detoxify, which is a system for predicting toxic comments, and which performed really well on all three of the Jigsaw comment challenges. If I click on this, I can go in the code and I can see how it's using Lightning. And I can also then later, if there are additional new flags or new different ways to optimize my model, I can play with those as well. And I can always take advantage of the new latest and greatest best practices by just changing here in my trainer the arguments. I don't have to go and figure out, override and change and modify complex code. And if I want to understand what the model is doing behind the scenes, it becomes a lot more readable. So I understand exactly how the forward function is working. I understand exactly how the architecture is. If I want to say, okay, how does this thing train? Okay, so it takes the batch, runs my forward classification, then it calculates cross entropy loss using binary cross entropy loss. And I can override that. I can maybe, if I want to take this model and I say, okay, maybe binary cross entropy loss with a focal binary cross entropy loss, because I have a new data set that's unbalanced, instead of having to refactor and figure out how everything works, or take the weights of a model that's just pre-trained, but it's really hard for me to override, I just go here and I just modify this loss function and apply the loss function I want. And now I have a new model that I can configure and play around with as a researcher. So in addition, we have a ton of really cool community projects. I'll call out a couple other ones. One is an implementation of MALBERT. So this is a state-of-the-art representation learning model for learning molecular structures. The AI2 Longformer, which was made like a lot of headlines a couple months back for being a model that enabled wider spans for text processing. And also one of what's going to be one of our first community highlights, and I'm a really big fan myself of Queen's Gambit on Netflix. So this model done by a community member of ours, Shubham, essentially looks at chess notation and learns how to play chess without any understanding of the board, just as a language problem, just by doing entity tracking on top of chess notation. So it's really, really cool. So, and that's just in the natural language processing space. We also have for computer vision, you have implementations like sparse image captioning using transformers. The grand prize winner, and I actually even have a post of this, of a couple different grand prize winners for Kaggle challenges, but for this one, the Wheat Growth Challenge was using Lightning. Magic Leap developed this really cool project for end-to-end 3D scene reconstruction from post images. So you can give it a bunch of images and it can process the images and then generate a 3D model of the world. And even Facebook recently, they had a new blog post on this as well, but they were using Lightning to help optimize some of the research work they're doing on COVID prognosis. And I'll show one last thing as we transition to audio, because we were talking about audio before. So there are a couple really cool audio frameworks as well, like NVIDIA Nemo, that run on top of Lightning. So this is a toolkit for conversational AI by NVIDIA. There's Asteroid, which is a really cool open source toolkit built on top of Lightning as well, that enables different architectures for audio source separation and experimentation. There's some really state-of-the-art results on urban sound classification. And one of my personal favorite that was made by a close friend of mine, Teddy Coker, which enables you to do it's called PedalNet, and it enables you to do guitar effect emulation. So like if you're really into music and stuff, you should definitely check it out. And here's the post. I'll share the links at the end for different Kaggle winners that have been using PyTorch Lightning and the flexibility of PyTorch Lightning to take their models to the next level. So let's get back to the presentation now that we've seen some community examples. So I want to show, like before we talked about the audio demo, I want to show kind of what that code from before looks like when when I refactor it for audio classification. So here we have this, and one of the first things I did was I made sure to ask and I recommend this whenever you're doing open source. Open source is a collaborative space, and it's really important to be open and transparent. So the first thing I did is I commented and made sure to get the author's permission. I didn't want to just take code and refactor and play with it. Even if it's open source, it's always important to speak with people and attribute your sources. Once I did that, I went in and I made my own version of this code and refactored it for PyTorch Lightning. So the first thing I did is I defined a data set within with using the PyTorch traditional data sets. This is to load my data. Here I have my transforms and what I need to load to get each item. Then the next thing that I do is on top of that, I define a PyTorch Lightning data module. So what this does is this helps me standardize, as we're talking about, all the things like my seeds, my batch sizes, the number of workers for my different data modules, for my different data loaders. It also enables me to standardize my splits between test, validation, and train, the number of classes and everything that I need. It also enables me to standardize any of the pre-processing code that I need for generating the different spectrograms. So in audio classification, one of the traditional methods that we do to do general audio classification is we take, and I can actually show this here from the blog post, is what we do is we take the audio, we turn it into a wave, and then we visualize that, and then we turn it into a spectrogram, and then we save the spectrogram as an image. And then the reason we do this is when it comes to transfer learning on audio, we have a lot more image data, models that are trained on images than we do on raw audio. So we try to take advantage of the features that we learned on images to do classification on the different visual differences between audio sources. So this is a strong traditional method for doing audio classification. And what you can see here is once I've done this, my model becomes super simple. So here, all I need to do is I can just take Torch Vision models. I take the model that I want here, comes pre-trained. I can set up whatever losses I want. So in this case, cross entropy loss. I'll treat it as a categorical. I can have my optimizer. This is what essentially enables my model to learn. I define in my step function what to do, what's a forward step. And then from there, I have my training step function. So this takes in my batches of data and it calls my step function on it. And I also have a validation step that I can do. So that way I can log my validation. And when I do self.log, you can see here that PyTorch Lightning manages the logger. So this can go out to TensorBoard, and it could go out to weights and biases, or it can go out to Azure ML or any place that I want. It becomes generalizable and more robust. And then here, when it comes to training the model, all I need to do is I define my data module. I define my audio classification model. I just pass it to my trainer. And then I just trainer.fit. And at the end, then I can just test out the model. So let me go back to the presentation. Hopefully, some of you who have some experience with machine learning and deep learning and different frameworks, that you got a lot of value on this. I recognize that there might be some in the audience here who are a little bit newer to the machine learning and deep learning space. And so for you, I also want to make sure that things are addressed and show you how you can get started and take advantage of some of these best practices. And one of the things that I would say personally is that Lightning is great for those who want to get the most out of PyTorch. But what if you just want to get a quick model and get started? So one of the challenges that I had when I went and refactored this code is I had this model. I had some code here that was actually pretty cleanly maintained, but it was very hard for me if I wanted to take this code and train it on multiple GPUs. I couldn't. It would have meant that I had to refactor and add a lot of complexity into this database. So I refactored it into PyTorch Lightning, and now it becomes really easy for me to do distributed training, to run this on TPUs, to take advantage of whatever I want. But still, there was some overhead for me. I had to convert this over. And when we think about audio classification, right? We said audio classification there's some pretty standardized patterns, right? So from a research perspective, I want some freedom and flexibility. But at the end of the day, I'm taking audio, I'm turning it into an image, and I'm loading an image classification model. Standard image classification, that's been done a million times. There are best practices for that. Why should I have to create my own modules for that? I should be able to just get a quick baseline. And this was one of my big frustrations in the beginning before I joined Lightning. But recently, we addressed this with a new framework called Lightning Flash. one second here. So what Lightning Flash enables is it enables you to get to a quick baseline that then you can override and play with whatever you need. So here are the key features: is you get end-to-end deep learning on different on proven tasks in minutes. You have distributed training and inference because everything's run on the Lightning trainer. I get all of the advantages of the trainer, including distributed inference. It's completely customizable. So everything, because it's built on Lightning, even instead of just me getting like a model and not being able to do anything except for inference or train it, if I want to start modifying that model, if I want to change the loss function, I can just open up and override the backbone with my own model or override different components in it. And you can even bring your own Lightning modules or Lightning modules from the community and integrate them as your own backends. So here are the 5 steps for getting started if you're not a deep learning expert and you want to just get a quick baseline. But also, if you are somebody who's really deep or a machine learning or deep learning researcher, this enables you to quickly get a baseline so that you can compare or get results on different data sets. And then once you have that baseline, you can then start overriding and experimenting without having to start from scratch. So the 5 steps is the first thing to do is choose your task. Here are 3 example tasks as well. We have image classification, sentiment analysis, and tabular classification. There are other ones as well, such as summarization, translation. We have object detection, and there are new tasks we're actively working tirelessly to develop new tasks such as graph classification, and I'll show you my prototype implementation of audio classification very soon. The next thing I need to do is load my data set. Once I've loaded my data set, I choose my model backbone. So there are all sorts of different machine learning architectures that I can apply to different tasks. So for example, we talked about like the traditional hot dog, not hot dog, or cat versus dog. There are a lot of different backbones that I could try, like Inception, MobileNet, ResNet, Suave. Here I can just choose and play around with whatever I want just by changing the backbone. And then what I can do is I can fine tune. So I can take the model, I can do transfer learning, I can choose to freeze weights, I can choose to unfreeze weights when I do the fine tuning. I can train the architecture from scratch, and all of that's configurable with very simple basic API. And then once I've trained my model, I just predict and I have a model that I can use. So I'll show you my sample implementation of what this would look like with my audio example. And then we'll move on to the next step. So if you'll remember, we had this large code implementation that's actually pretty clean, but like, for example, if I wanted to add TensorBoard or I wanted to do all these configurations, it would have been hard for me to do. I have my Lightning configuration that I built. Now what's cool is but I still had to do all this overhead here, right? I had to define the dataset class. I had to define a data module. I had to define a model and choose model architectures. With Flash, it becomes really simple. All I need to do is I install Lightning Flash. The first thing I do is I import Flash. So I do import Flash core fine tuning, freeze, unfreeze. I get my, from Flash Audio, I import spectrogram classification data, spectrogram classifier, the ESC, which is a traditional sound classification data set to download that data, 2 helper functions for converting from WAV files to spectrograms, and another function that will help me display the spectrograms. I download the files of my data set, and that would download them locally. Then the next thing I do is I just use my spectrogram classification data from folders, and I provide the folders of the data set where my train files are, where my validation files are, and if I have them, also I can put in test folders, test validation, test data set here as well. For this specific case, this data set didn't come with a test folder, it only came with a train and a valid. So I put the split here. And also within And then once I have this data, I can train my model. And what's really interesting here as well is that these loaders for loading your data, they come with a bunch of other really nice functionality in there, like they can manage splits for you, and they can do a bunch of overhead boilerplate and abstract that out for you. So then the next thing I want to do is I train my model. So I just declare a spectrogram classifier. I choose whatever backbone I want. So whether that's ResNet, ImageNet, in this case, Swab ImageNet, which is a self-supervised model trained on Swab, called Swab trained on ImageNet. I can also use ResNet, MobileNet. There's a whole list of different backbones I can try, and new ones are going to be added all the time. And then I just declare my trainer. So because it's built on Lightning, I get all the features of Lightning. So if I want to do for 100 epochs, I do for 1 epoch. If I want to take advantage of the GPUs, I just do GPUs. If I want TPUs, that's simple. And then I have TPUs. Exactly as we saw before. Then we do trainer.fine-tune. I pass in my data module, and I have all these different strategies that I can use for fine-tuning. So freeze, unfreeze. What this does is for 1 epoch, it will unfreeze the model. So it will update all the weights when I'm training. And then after that, it will freeze those weights and only freeze most of the weights and only update the classifier at the end that I append on top of the model. And then here, when I want to test my model, I just run trainer.test, and I'll get any metrics I want. I can configure all the different metrics like recall, accuracy, precision, and there's new metrics through PyTorch Lightning that are being developed all the time. I can do trainer.save checkpoint, and then I can load this model, and I can predict on new data. Extremely simple, just do model.predict, or I can use the trainer to predict, and I provide the trainer my model and a new data set or a new data module on a different set of images, and then I can take advantage of distributed training across clusters of GPUs, TPUs, and you name it. So I hope you can see like how much simpler this is versus this versus this. And that's what Flash enables. So I'll show you in the repo here. PyTorch Lightning Flash. It enables me to go in and very quickly get baselines for all sorts of tasks. And we have samples here for image embedding, text summarization, tabular classification, object detection. If you're deep into or you're technical and you have a background in deep learning, we're also going to be doing a community sprint very soon. So it's an opportunity to get involved. And then the last thing that I want to show here, and let me just continue, is how do I train at scale without all the overhead of infrastructure? So if I wanted to train on the cloud and I want to train on 100 GPUs or 200 GPUs, now there are a lot of frameworks that enable this. Azure ML is a great framework. SageMaker is another good framework. GCP also has ML offerings, but there's a lot of overhead that I need to think of in terms of like, how do I architect, set up the API, set up my workspace? What Grid does is Grid provides an interface to kind of enable you to seamlessly train hundreds of machine learning models and experiments from your laptop without having to deal with all the configuration and overhead of the infrastructure on the cloud. So imagine here, you can see I have this Python script that's using Lightning. I can just change it to Grid GPUs. I can choose the uniform learning rate. And just like that, exactly like how I would train on my local instance, it now spins up 20 different configurations on whatever backend that I want. So that Grid is in early access now. And if you want to sign up for the wait list, You can do that at grid.ai/sign up. I'll conclude now, and then we can open the floor to some questions. So number one is contribute to open source. It's really awesome. I don't think I have to convince you of that. And if you're interested in contributing, there's a how to contribute guide in our repo and on our docs as well. And I'd be happy to work with you with that as well. And we'll make sure you get some cool Lightning swag. To summarize, PyTorch Lightning provides a lightweight research framework with full flexibility, reduces the boilerplate significantly, and enables for you to run your code on any hardware without modifying each of the individual calls within your scripts. So with that, I'll open it up to questions.
Thanks, Ari. That was very thorough and amazing. And I have not used PyTorch Lightning personally, but like after this, I'm gonna have to go play with like refactoring some of my PyTorch stuff to see. It was really neat how you could do like with the params and just to like override, like if you want GPUs or TPUs or whatever you wanted, like in just a parameter. I think you called it something else, a flag for training or whatever the correct language is there. But it was just really cool how it really simplifies a lot of things that were difficult before. And so one of the questions that we had was, if you've already like written a bunch of PyTorch stuff, how hard is it to kind of factor this stuff out into that boilerplate? You showed us a little bit.
I'm really glad that somebody asked that question, because I actually cut that out of the presentation. But since you asked the question, I can show you.
Awesome.
So here, one second. Let me just unskip these slides for you. And I didn't want to get too technical without somebody actually explicitly asking for it, but it's pretty simple. So the first thing that you want to do is you want to move out like so the way PyTorch Lightning works is you have your data module and you have your Lightning module. What those modules are, they're essentially interfaces that you can implement. So you just organize your code within those interfaces. I can actually show you here, PyTorch lightning.ai. We can go into the docs. Sorry, that was the GitHub. And go into the docs. And so if I have my Lightning module, my data module here, it actually shows there's a nice little GIF that shows.
We're not seeing your screen.
Oh, sorry.
It's okay.
Thank you for letting me know. Okay, let me. All right, one second. You should see my screen shortly. There we go. There's my screen. Okay. So here, if I go into the docs, I have my Lightning data module. And so what the Lightning data module is it's essentially the simple class with organized hooks. So I have my initialize, I have my setup. This is where I would download all my data, or there's additional hooks that you can put in as well, like my prepare data. This is where I would actually download the data. Then I have my setup where I'd go in and manage the different splits and trains. I have my train data loader, my val data loader, and there's all this documentation. So essentially what I would do is I would take my code that's in PyTorch right now, and where I have this functionality, I just move it over. So where I download my data, I move it over. Where I apply all the transforms and split, I move that into setup. Where I want to do, where I have my data loaders, so now I split these up. Instead of managing them myself, I have one for validation, one for test, and then all the rest here, all this boilerplate, Lightning takes care of for you. So I can actually here, if I show the script in the beginning, pause here so we can kind of see some of that. So like here, notice you have this if global rank equals 0. Why do you have that? Well, in this case, this person is trying to do distributed training. So they don't want to download the data every single time. So they now need to manage all these forks and complexity. Once you've taken these components and transferred them over, you don't need to do that anymore. So that would be for the data module. And you can see we actually have, so you do that first for your data, and then you would do that for your model as well. So here, what I can actually do is I'll show you in the slides. I'll walk you guys step through the process. So here, the first step would be to move the computational code into a Lightning module. So we replace the NN, the typical PyTorch NN module. We swap that out and it becomes a PyTorch Lightning module. That essentially enables you to access all the hooks and the interface of PyTorch Lightning. The next thing we do is we configure our optimizer. And now the parameters are part of the Lightning module. And we want that for reproducibility. So instead of it becoming here in instead of putting that just and managing that directly in the optimizer, it gets managed by the module so that if somebody else wants to take this code, they'll get the same results. Now we take the meat of the training loop. So in our training step, we can add self.log, so we can add and log anything that we need. We can add a validation step. And then we can also we remove all the CUDA calls because again, all the compute is managed by Lightning. So we just remove those. And then this becomes your Lightning module. And you'll notice in the forward here, because Lightning manages the optimizer for us, this takes out all these things where you have to do optimizer.step, or you forgot to type optimizer.step, or all these different things, and then your model doesn't converge and you have no idea why. You know, optimizer.0grad, or all these common mistakes that you have when you're training with PyTorch, Lightning abstracts that out all for you. So addition to this, you have hooks, which then if I want to do additional things, like for example, I want to, if I want to actually make these calls myself, I don't have to, but if I want to, I can tie into the hooks and I can override that logic for when I need to have that flexibility if I'm doing research or something off the beaten track path. And then what's really cool here is, like, typically you have this huge training loop, you can kind of just delete the training loop then. And then instead of the training loop, you use the Lightning trainer, and here you just do fit model. Provide your data in, or you could provide your data in. So you actually can pass in your data directly as data loaders. It's not opinionated, but if you want here, you can actually take this data code that we talked about before, you put that in a Lightning module, and then it becomes standardized. So I put in trainer.fit data module, and then I have all the flexibility. So if I want to run that now as multiple GPUs, I just put in GPUs equals as many GPUs if I want. If I want to do, if I'm on an Azure cluster and I want to run on multiple nodes in Azure ML, I just have to register in the Azure ML cluster all the default. I actually have a blog post on this, so I need to just register the Azure ML cluster, and then I can just scale this. So the same code that I have that runs on a CPU can run on a GPU, multiple GPUs, and all these other features that I talked about, you get just like that. So, all right, next question.
Yeah, that was really cool to see that it doesn't actually look that complicated to do the refactor.
No.
Like, that's neat, because with some of these things, it's like you have to put in all that time to get the benefit, and it's like, is that time with the benefit? But that was a really good explanation on how you can take what you already have, make a few changes, and then now you have all this added functionality. So love
exactly. That's actually one of our philosophies is, we have this really strong engineering deep learning research team, and our goal here is we want to take all the complex overhead on ourselves so that you guys don't have to deal with it. But if you want to deal with it and you are a researcher, we're not going to block you out. We're going to enable you to override and customize and do what you need to do.
So I actually had a question when you were showing Lightning Flash and Lightning, and you were showing that, like, it was really, really simple to do, like, an image classification with audio data using Flash. And you could still do all of, like, the overrides that you could do in Lightning. So if I'm going to do an image classification, why would I choose Lightning or Lightning Flash? Like, what would be the reasons for
Absolutely. So this is how I describe it. Is if I'm getting started, I use Flash to get a baseline. So there are hundreds, if not thousands, of different variations for different types of machine learning tasks. Some of them are more experimental, like in reinforcement learning, which we actually support with Lightning as well. And there's some examples of that in Bolts. Some of them are more common that we see a lot. So for example, image classification is a pattern we see a lot. Object detection, pattern we see a lot. For those patterns, it doesn't necessarily make sense for me to write, if I'm not a researcher, even if I am a researcher, to just restart from scratch if there's already code out there. So the idea of Flash is it enables me to take my data, put it into a Flash task, and just iterate to get baseline results. And also, if I'm a beginner, that's a great way to start, because then I don't need to worry about what's the back end. I can just put in my data, I choose the task, and it will train. And we configure, we ourselves, I mean, we don't know for every data set, but we look across general data sets and we'll choose, and we configure our data modules to have as generalizable configurations as possible for most tasks. All right, so that's a great entry point and a great way to baseline. Where Lightning is for is then when you want to go off the beaten path, or you want to experiment, or you want to change things, then you can start overriding and changing what you need to do. So I know that we're a little bit over, but I'll give one example of this just before we sum up. Is today, for example, and again, I love Keras. Like, it's one of like, it's how I started. I started with TensorFlow. Well, I started with scikit-learn, but when I started in deep learning with TensorFlow and Keras, but one of the big challenges that I've had in Keras models, for example, is I have this model. I take it from a model hub. I train the model. It works. Everything's great. But if I want to now change the loss function of a pre-trained model, I can load that model, but it's very hard for me to change that. Whereas here, everything's accessible. It's overridable. So
yeah, it kind of helps, like with that, grabbing different code and running it, and you have to go through and reconfigure everything to work, where this should be kind of more of like a grab and run, style.
Yeah. And it's about all those things we talked about earlier: reproducibility, readability, reusability, and just enabling people to iterate as fast as possible with the machine learning models. That's, one of the biggest challenges today is, like, if a new state-of-the-art model comes around, it's become a lot more trivial to find a GitHub implementation of, a new state-of-the-art model, clone it, and run it. But if I want to start like actually experimenting, changing, or building on top of it, that's really hard to do. And Lightning makes that a good amount easier.
Okay, so we're going to have one last question here that somebody asked about contributing. They asked kind of what the community's like, and what kind of contributions are you looking for? I know you mentioned there's like a hack coming up or something for contributing, but yeah, people want to kind of know how they can get involved.
So absolutely. So there's going to be like a couple hacks like that. There's a community sprint that's going to be coming up for people to contribute tasks to Flash. Now, like, again, that's targeted towards people who there is going to be an application process, because some of the things there are pretty deep and pretty technical. So like, one of the ways to get noticed or to be approved for that is to build on top of Lightning and show us what you can do or what kind of tasks you can build out. In addition to that, like, as we go forward, like, that's why I'm so excited to be ahead and create a developer advocacy department, because I'm hoping to do a lot of really cool events. So once we have more Flash tasks and we have this underlying API baked out, then we'll do events where we'll help encourage people to build on top of. I'll show people how that they can contribute more cleanly. I'm going to be writing a lot of documentation as well. If you are at that technical depth and you do already want to start getting to contribute, all you have to do is you go to the PyTorch lightning.ai, and here under contribute, we have all the documentation that you need in terms of the contributor guide. Also, when you're getting started and building out and playing around with, if you ever get stuck, we have a Slack community where we have members of our core team on call and we divide up shifts throughout the day, and people try to get to any question within the same day, sometimes even within like minutes of you posting it.
That's really cool. Well, thank you so much. That was super informative, really interesting. I think a lot of people have ideas on how they can go start using Lightning and Lightning Flash. And,
Oh, you really should, because it's amazing.
and then I will let Eileen, I'm sorry, not Eileen, Annaline.
Yes.
How do I say it again? I'm so sorry. Annaline? Okay. I'm so
Yes.
sorry.
Thanks a lot. These Dutch names are not always easy to pronounce. Anyway, thanks a lot for the presentation. I loved it, especially it really ties in very well with the whole MLOps and data ops that we're now seeing a lot these days. And yeah, I will definitely try it out. You have triggered my attention. One more thing I'd like to mention is that we will be back on March the 3rd, same time, same place. And next week's topic is open source documentation and tools. Thank you for joining, and
Thanks.
see you next time. Bye.
Bye.